AP Chemistry, we are up now to day 79, and we're really going to get into buffers and how to create a buffer today. Again, the definition of a buffer is it's a combination of a weak acid and its conjugate weak base that can neutralize either a strong acid, that would be the conjugate weak base, or a strong base, that would be the conjugate weak acid, if they come into the solution. And what they can do is, for at least a limited amount of time, they can hold the pH steady. So let's go ahead and see how those are created here. So we're going to review a few concepts, some of the things that we maybe haven't talked about since before even the break. Okay, so strength of an acid versus the acidity of a solution. So the strength of an acid is measured by how completely it dissociates a proton in pure water. So the strength of an acid is measured by its Ka value, which can be expressed as pKa, and that's simply by doing the same thing to Ka that you do to hydronium ion concentration, which is take the negative log. And that will give you something called a pKa. Again, why do you do that? Because it just gives you a scale that's a little more user-friendly. It's not a lot of exponents and very big and very small numbers. It's just a nice scale that's kind of in the normal range of numbers that we're used to working with every day. Now, the acidity of solution is measured by the concentration of hydronium ions, H3O+, in the solution. The acidity of the solution is measured by pH and is determined by, first, the strength of the acid, that is the Ka value. It's how strong the acid is, but also how much you use. So you can produce more hydronium ions in a solution by using a lot of a weak acid as compared to maybe just a very small amount of a strong acid. You could end up with a lower pH. Remember, lower pH means more acidic. You could end up with a lower pH by using a weak acid if you use a lot of it. So the acidity of the solution depends on not just the acid, but the acid in the water together. So the acidity of solution is measured by pH. So how do Ka and pKa compare to pH? So here's the metaphor I used some time back. Let's see if it helps you. So a 6th grader can lift 5 skateboards up onto a shelf. A 12th grader can lift 10 skateboards up onto a shelf. So this represents the intrinsic strength of a 6th grader and a 12th grader. In other words, that would not change. It's how strong each one of those are. This is comparable to the Ka value of an acid. It compares equal amounts, and it's what's called their intrinsic strength. So the Ka value for a particular acid doesn't ever change. For example, acetic acid has a Ka value of 1.8 times 10 to the negative 5th. You can look that up in your book. You can look it up on Google. It never changes. No matter what problem you're doing, that's the intrinsic strength or dissociation constant, Ka, for acetic acid. So Ka is a characteristic of the acid only. Now, which can lift more skateboards, 6th graders or 12th graders? Now you need to know how many 6th graders and how many 12th graders. So if we have 18 6th graders, they will be able to place more skateboards onto the shelf than 2 12th graders. This is how pH works. So pH depends both on the intrinsic strength of the acid, Ka, but also on the amount of acid. That's measured in molar concentration. So pH is a characteristic of the solution. That's the acid and the water together. It's how many hydronium ions. It's the concentration of hydronium ions in the solution. So what is pKa? So here's a review of the acid dissociation constant Ka. Ka is the equilibrium constant for how much an acid dissociates. Ka can be expressed as the concentration of hydronium ions over the initial concentration of the original acid. So there it is. Okay, that's the equilibrium equation known as the law of mass action, and that's for an acid. So the right side of the equation, the products, would be the H plus and the A minus, the hydronium ion and the conjugate base. And what you start with over on the left side of the arrow, the reactant, would be the acid, HA. For a strong acid, dissociation is 100%, or we're going to say very close to 100%. So the ratio is a very large number. You'd have a very large number on the top and almost 0 on the bottom. Of course, if you have 0 on the bottom of a fraction, you can't do the math on it. It's undefined. But we're going to say something very close to 0. So that means it's going to approach infinity for a strong acid. For a very weak acid, the dissociation is tiny. So the ratio is a small number over the HA, so that's going to get very close to 0. It's not going to be 0. It does dissociate, but we're just going to say it approaches 0. So the range is between 0 and infinity. Okay, this means that Ka values can range from, and I'm just picking numbers here, 10 to the negative 20th all the way up to 10 to the 20th. Something very, very tiny, close to 0. Something very, very large, approaching up to infinity. So this is a much wider range than the hydronium concentrations that are used to compute pH. For this reason, chemists use a p-value for the acid dissociation constant. And there it is. This value pKa is the negative log of the Ka value. So let's just get an idea of what those could be. So example, what is the pKa of weak acid hydrofluoric acid? Well, you can look up in your book that the Ka for hydrofluoric acid is 6.8 times 10 to the negative 4th. If you take the negative log of that, you end up with 3.17. What is the pKa of strong acid hydroiodic acid, HI? Now I'm going to kind of make up these numbers somewhat, but let's assume that you have 10 molar and that 9.99 of that concentration dissociates, breaks into a hydronium and conjugate base, and only 0.1% remains as HI. We can't have it 0, or we can't, as I said before, we can't do the math on it. So you have 9.99 over 0.1. 999, and that would give you a pKa of negative 3. So lower values of pKa represent stronger acids, and in fact strong acids have pKa's in the negative numbers. Okay, I'm going to derive a couple of equations we're going to have to use. You do not need to do this on a test. You do not need to do it on the advanced placement test. I'm really doing it as a review of rice tables because we haven't seen one of those in a while. So let's look at this rice table. You have your short form, your abbreviated acid dissociation equation. You start with an acid, the proton dissociates to become an H+, and then whatever is left of that acid other than the proton is the A-. That's the conjugate base. So we start with some concentration of HA, whatever it is, could be 1 molar, could be 0.1 molar, whatever. We're going to assume that we don't start with any hydronium ions or any conjugate base in the solution in the initial line. Now remember how we do the change line. It's always a variable there, an X. On the reactant side, it's a negative because you're using up the reactant. That's on the left side of the arrow. And you always use the coefficient in front of the X that's in front of the original equation up above, so it's 1. And with acid-base reactions, it's always going to be 1. For the hydronium and the conjugate base over on the right, you're going to add an X because those are increasing in concentration, and it's also 1 because of the ones up above. So when you subtract the reactant side, it's HA minus X, and when you add on the product side, it's 0 plus X is X for both the hydronium and the conjugate base. So now we're going to set up the equilibrium equation, the law of mass action. Okay. So here it is. Actually, I should have put that up earlier. Here's how to derive the shortcut equation of the pH of a generic weak acid reaction at equilibrium. So there we go. The product's equilibrium line on the product goes on the top, X times X. You also put as exponents the coefficients, but they don't have any. I mean, they have a 1, so you don't have to put that up there. So it's X times X, and down on the bottom is the reactant side. It's HA minus X. Now we're going to use the simplifying assumption, assuming that X is much less than HA, so it goes away. And so now you have what you see there. Now we're solving for X, so we're going to multiply both sides by HA. There we go there. Those cancel. And what you have is X squared equals Ka times HA. Now I'm going to reverse the equation. I'm going to flip it around the equal sign, and I'm going to take the square root of both sides. I'm going to do both of those in the next step. So there you go. The X squared comes over to the left, and you take the square root of both sides. So now you have X equals the square root of Ka times Ha, your original acid concentration. And now we're going to take the negative log of both sides. Again, you can do anything you want. Well, actually, we're going to do a substitution first. We see that what X equals that we're interested in is the hydronium ion concentration, because that's what's going to determine pH, is hydronium ion concentration. And that's represented by X on the equilibrium line up on the rice table. So we're going to substitute the H plus for that X. So now we have H plus, hydronium ion concentration, equals Ka times Ha. Now we're going to take the negative log of both sides. Anything you do to one side is legal as long as you do it to the other. So take the negative log. Okay. And what you see there then, what is that on the left of the equal sign there? Well, negative log of the hydronium ion concentration is pH. So that's going to give you the formula pH equals negative log of the acid dissociation constant times the initial concentration of the acid, assuming that you can use the simplifying assumption, and we always make that assumption. You can always cancel that X out there. Okay, so that's the first equation. Again, you don't have to do this on a test or on the AP. I want you to it's just really a review of a rice table and showing you how we get to this equation. All right, now there's an equivalent equation for POH if there's only weak conjugate base, that's A minus, concentration of A minus, and no initial conjugate acid. So in this, you see this is an acid equation. You start with a base on the left, then you add a proton. It accepts a proton from a water molecule, and that produces HA, the conjugate weak acid, and then the hydroxide ion, which is the characteristic of a base. It produces hydroxide ions, OH minus. So we do the same thing. I'm not going to go through the whole equation, but the equation looks very similar. For POH, it's negative log of the base dissociation constant Kb times the initial concentration of the weak base. Okay? And the following relationship is your acid-base from your acid-base roadmap, is that Kb equals Kw over Ka. So if you need to know what Kb is, books don't give you Kb values. They give you Ka values. So how do you get to the Kb value? You use that formula. Kw is called the autoionization of water constant, and that's 10 to the negative 14th, always in this class. It's going to be 10 to the, so it's 10 to the negative 14th divided by the Ka value that you could get out of your book, and that'll give you the Kb value. Okay. Now, here is how to derive the shortcut equation of the pH of a generic weak acid conjugate base buffer solution not at equilibrium. So now we're dealing with a situation where you do have both the weak acid and its conjugate weak base. So if we look up at the initial line, you have your initial acid, then you have some hydronium ions in solution, and then you have some conjugate base ions in solution also up on the initial line. Now we're still going to subtract 1x on the left side and add 1x on the right side, and you end up with HA minus X in the equilibrium line for the acid. You end up with hydronium ion plus X on the right side, and you end up with the conjugate base plus X on the right side as well. So now we're going to set up the law of mass action the same way we did before. There it is. So convince yourself that that's what you see up there on the equilibrium line. The reactants are on the bottom, and the products are up on the top. Okay, so here we go. So you can cancel all of those X's. Just assume they're very, very small. And what you have here is H plus times A minus over HA. So there it is. Now we're going to multiply both sides by HA and divide both sides by A minus, all in the same step. So on the right side, the A minuses cancel out and the HAs cancel out. And you have them now over on the left side, Ka times HA over A minus. That's your original concentration of your acid over your original concentration of your conjugate base. So now you're going to solve for the H plus. Well, it's actually already done that, and we just rearranged it, put the H plus, the hydronium, over on the left. Now again, you're taking the negative log of both sides. Anything you do to one side is legal as long as you do it to the other. So we're taking the negative log. Now look over on the right side. There's a principle of logs. and it is that the log of A times B equals the log of A plus the log of B. If you go to your units of measure sheet, I believe it's called, in your packet, just go through your packet. It's the one with all the different units of measure on it. Log principles are in that, and you will see that principle. So again, log of A times B equals log of A plus log of B. In this case, we have a negative log, so it's going to be a subtraction. So we come down here and we rewrite the right side the way I just said. So it's the negative log of Ka minus the log of Ha over A minus. All right, so now you should recognize what's negative log of H plus and what's negative log of Ka. So there it is. Negative log of H plus is pH. Negative log of Ka is pKa. And now I did another little trick, simply because this is the way I'm used to seeing the equation written. If you have a log of a ratio like that and you flip it, you take the reciprocal. So you take the HA over A minus and you take the reciprocal of it, then you change the sign in front of the log from a minus to a plus. So that's what I did over there with the log. I put the base on top and the acid on the bottom. This is called the Henderson-Hasselbalch equation, and it's a very important equation coming with regard to buffers, and you're going to be using it in this lesson. So the Henderson-Hasselbalch equation is used to calculate the pH of a solution in the buffer range if the pKa and concentrations of the conjugate a weak acid-base pair are known. You're going to find out what the buffer range is here very, very shortly. So Henderson-Hasselbalch equation is, as you see there, it's the base over the acid. 3 important points about this equation. It only applies to the buffer region of a titration curve. Both weak acid and weak base must be present in the solution. In other words, in that equation, if either the base or acid is 0, then the equation is undefined. You can't use the equation. You have to have both in the solution. And that actually should be number 3 down there. The acid and base must be conjugates. Can't just pick any weak acid and any weak base. They have to be conjugates. So here's a summary of the equations. To find a strong acid, the pH of a strong acid, it's simply the negative log of the hydronium ions. That's one we've been doing since the very beginning. To find the pH of a strong base, you find the pOH, which is the negative log of the hydroxide OH concentration, and then you subtract that number from 14, and that will give you the pH. Now the weak acid HA at equilibrium is the one we derived just a moment ago. There it is. The weak base B at equilibrium is the one that we showed you. You take the weak base equation, you come up with the pOH and subtract that from 14 to get the pH. And finally, weak acid HA and its conjugate base A minus in the buffer region, that's Henderson-Hasselbalch. There must be both HA and A minus to use Henderson-Hasselbalch. So you might want to jot these equations down, okay? And I would recommend that. I'm going to ask you to do that in class and on the assignment. It doesn't hurt to memorize them, but you should definitely have them written down somewhere because you're going to use them. Okay, now we're going to do a titration like we did last week, except now that was, if you remember, a strong acid and a strong base. That's an easy situation because when you put a strong acid together with a strong base, the hydronium of the strong acid, the hydroxide of the strong base get together and neutralize and form a water molecule. And you're done. That's it. That's easy. Until one of them runs out. And whichever one does not run out first, then the solution will start to become of that character. In other words, if you run out of the hydroxide first and you still have hydronium, then it's going to be acidic, an acidic solution. If you run out of hydronium first, the acid, and still have hydroxide, the base, then it's going to become basic, OH minus. But until they run out, they're just going to neutralize into water molecules. So that's a simple situation. This situation is a little more complicated, so we're going to walk through this. So we're going to take acetic acid, CH3COOH, and that's the weak acid, and we're going to drip, 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 do a titration, and put sodium hydroxide into that. So one thing we know is that the sodium is immediately going to break off from the hydroxide and go off to the side and be a spectator. So what we're really putting into the solution is hydroxide ions, OH minus. Okay, so let's go ahead and start. Initially, we're going to start with 1 molar of the acetic acid. There you see initial. And we're going to start with none of the sodium hydroxide. We're eventually going to keep adding sodium hydroxide until we have 2 moles. I'm going to use molar and mole interchangeably. If we assume that it's 1 liter of solution, then you can do that. But since it says mole, I'll say mole. So you go ahead and do that. You start like that. So what's the initial pH? Well, you only have a concentration of a weak acid, so you use the weak acid equation. It's the negative log of the Ka for acetic acid, which is 1.8 times 10 to the negative 5th. You can look that number up in your book or online. The concentration, we're looking at the final, where it says final for acetic acid there, 1 molar is 1. And you take the square root of that, then negative log, and you get 2.38. So your initial pH of the solution is 2.38. So we use the weak acid shortcut equation, and there you see it right there. Okay, now we're going to plot, and there it is. So the final state, there was no change. There's a 1 molar concentration of acetic acid. We use the acid shortcut equation to calculate the pH. There it is again. Plug in the numbers again. Ka for acetic acid can be looked up in your book. It's 1.8 times 10 to the negative 5th. That's the Ka of acetic acid. And you get 2.38, so that's where we plotted that first point. Now we're going to the second line. And now what we've done is we've added a 1/2 mole of sodium hydroxide. So there's still less sodium hydroxide. Remember, that's the invader base. And the acetic acid is the defender weak acid. So the defender weak acid is going to totally neutralize that hydroxide there. So if you put in 0.5 moles of NaOH, you have 1 mole, that's more of the acetic acid, then all the NaOH is going to disappear. Okay, it's going to become water molecules, but you're also going to use up 0.5 moles of your acetic acid. So at the end, you have 0.5 moles of acetic acid. Now, once the acetic acid donates that proton, that H, over to the hydroxide to turn it into a water molecule, then the acetic acid turns into its conjugate base, which is over there on the far right, CH3COO-. So now you have concentrations of both acetic acid, the weak acid, and the acetate ion over on the right side. So since you have both of those, well, let's just read this. There are equal concentrations of weak acid, weak base. So this is where you want to buffer a pH of 4.75, and this is called the half equivalence point. So we're going to go ahead and use Henderson-Hasselbalch. There is both weak acid and weak conjugate base present. This is the buffer region. Okay, use Henderson-Hasselbalch. There it is. So we plugged in the numbers. And whenever you have equal amounts, remember we said back in previous lesson, you want to have equal amounts of the weak acid and the weak conjugate base. Why? Because you want to protect the solution both from the acid side, that would be the weak conjugate base, and from the base side, that would be the weak conjugate acid. And you want equal amounts of both of those. And so that's ideally where you want your buffer to be, is equal amounts. And that's what we have right there. It's called half equivalence because you're halfway from having all of your acetic acid, 1 mole, to having none of it. That's 0 moles. So you're halfway there. That's called the half equivalence point. And when you take the log of a number over itself, any number over itself, you get 1, and that's going to be 0. The log of 1 is 0. If you don't believe me, just go to your calculator and prove it to yourself. The log of 1 equals 0. So that means that 4.75 plus 0 is 4.75. So what that means is you want to create if you want to buffer a pH of 4.75, you pick a weak acid that has a pH, or a weak base, but a weak acid in this case, that has a pH of 4.75. So you want your pH, let me say that again. If you want to buffer your solution with a pH of 4.75, you want to pick a weak acid with a pKa of 4.75. So basically the rule of thumb is whatever pH you want to buffer the solution at, you find an acid that has a pKa of that same number. In this case, acetic acid has a pKa of 4.75. And there you go. So that's what you want to choose. If you wanted to buffer your solution at around 8.2, you'd go and you'd look up an acid that has a pKa of 8.2. You want the pKa to equal the pH. That's the acid, the weak acid that you want to choose for your buffer. Okay, so we're going to push on here. This is a slide you should really study. Be sure you understand what the half equivalence point is and what the significance of it is in terms of creating a buffer. Okay, so this is the half equivalence point because half of the weak acid, acetic acid, has been used. The half equivalence point is where you want the buffer. So there we see it right there. That's what we want to buffer with acetic acid. Okay, now we're on to the third line. So now we still have both a weak acid and its conjugate weak base. You can see those in the red boxes. So you're still going to use Henderson-Hasselbalch. As long as you have some of both, you use Henderson-Hasselbalch. You plug it in and you get a pH of 5.70. Okay, so use Henderson-Hasselbalch, pH of 4.75 plus the log of 0.9 over 0.1, and that's going to equal 5.70. So the pH is sneaking up a little bit as you keep adding the base, because base is going to drive the pH upward. Henderson-Hasselbalch can only be used in the buffer zone pre-equivalence. Okay, we're going to define all those later, but just what you see there is called the pre-equivalence because you haven't gotten to the equivalence point yet. There must be both acid and conjugate base present to use Henderson-Hasselbalch. Now we're on to our fourth titration. So now you see that we've used all the sodium hydroxide that was put in, and now you've used up all of your defenders, all of your weak acid defenders. They've totally been wiped out. So you have a 0 for your weak acid and you have a 0 for your sodium hydroxide, although you're going to add more sodium hydroxide in subsequent steps. So that's called the equivalence point because the amount of weak acid and the strong base are equal. So now you have to use kind of a little bit of a long equation here. There is no acid remaining, so we must use the weak base shortcut equation and subtract that from 14 to get the pH. So you see down there in the yellow box, we have the weak base shortcut equation. So you need to calculate your Kb. It's not going to be given to you in a book. It's going to be 10 to the minus 14. Just go to your acid-base roadmap. 10 to the minus 14th divided by the Ka that we've been using, and that will give you the Kb of 5.5 times 10 to the negative 10. The concentration of A minus over there on the far right is 1. So you take the square root of that, take the negative log of that, and you subtract from 14. It's kind of messy, but anyway, that gets you the pH. And that's 9.37. So now you see, unlike a strong acid, strong base, which totally neutralized each other perfectly, and you ended up at the equivalence point with a pH of 7, well, of water right in the middle, totally neutral. Now you don't have a neutral pH at the equivalence point. Why? Because you have some of your weak base, conjugate weak base over there on the right, that 1 molar of conjugate weak base. You don't have any more strong base, you don't have any more weak acid, you just have that weak base, and that's going to make the pH up in the base range, which means up above 7. Okay, and we're going to plot that there. So the equivalence point is reached when weak acid CH3COOH is completely consumed. There is only weak conjugate base, acetate ion, making a weak basic solution. Now additional hydroxide added will make the solution strongly basic because there's no longer the weak acid defenders to neutralize it. So use the base shortcut equation and subtract. So first you compute the Kb, 10 to the minus 14th, over, that should be 1.8 times 10 to the negative 5th, gives you 5.5 times 10 to the negative 5th. Again, that formula is on your acid-base roadmap. Okay, and then you have pH equals 14 minus that, and that gives you 9.38, okay? Just a little bit of a messy equation, but there it is. Now we're going down to the next titration. Now we have no acid in the solution anymore. That we're done with the acid. But we now we added 0.1 mole of strong base. So now we have 0.1 mole of strong base. There's nothing there to neutralize it. And we still have that 1 mole of weak base over there on the right. So those two boxes are what are going to drive the pH. So let's read this. There is both strong base and weak base present here. However, the strong base will dominate the pH. So the CH3COO- can be ignored, and we can use the equation pH equals 14 minus POH. So we can use the strong base equation. That is negative log of the strong base of the hydroxide. So 14 minus that will give you 13. That's going to be your new pH. So you can ignore, when you have a strong base and a weak base together, you can ignore the weak base. It's just the strong base that's going to drive the pH and control the pH. Okay, and there we are. So no acid remains here, so we compute the POH from the NaOH and CH3COO- base concentrations. Since sodium hydroxide is a strong base, so its presence dominates the weak base, the acetate ion, and we can ignore the acetate ion. Once we have the POH, we can subtract from 14 to get the pH. So there we are. Okay, our fifth titration. Now we are all the way up to half a mole of strong base. So again, there is both strong base and weak base present here. So we will use only the OH, the strong base, which is 0.5 moles. And you go ahead and plug that into negative log of 0.05. You get your POH. So 14 minus POH is going to give you 13.7 for your pH. And finally, the last one is going to be the same thing. Well, let's do this one first. We plot it. Again, no acid remains here, so we compute the POH from the NaOH and acetate ion base concentrations. Sodium hydroxide is a strong base, so its presence dominates the weak base, acetate ion, so we can ignore the acetate ion. Once we have the POH, we can subtract from 14 to obtain the pH, exactly the same as the last step. And finally, the last titration. Now we're up to 1 mole of NaOH. We know we can ignore the acetate ion over there on the right. So it's going to be 14 minus the negative log of 1 mole. And that's going to give you a pH of 14. So you used all 5 of those equations somewhere along the way here. So again, it's just arithmetic. You just have to practice it a few times to get used to it. It becomes natural. So finally, 1 molar sodium hydroxide dominates the weak base acetate ion, and we can ignore the acetate ion. Once we have the POH, we can subtract from 14 to obtain the pH. Okay, so this flat area appears at the pKa of the acid. In this case, acetic acid, it's 4.75. In this range, small changes in the concentration, in other words, moving from right to left along the horizontal axis, do not lead to changes in the pH. That's what a flat line does. You can go left and right. It doesn't go up and down, or virtually not at all. And that creates the flat area. This means that you can create a buffer here, and that's called the buffer region. Okay, now we're going to see a summary of everything we just talked about. So first, we start at the initial point that we started with. You only have the weak acid, the acetic acid in the case of the example. So you're going to use the weak acid equation. There it is right there. You just plug in the numbers for the Ka of acetic acid or whatever your acid is and the initial concentration. That will give you the pH at the beginning. Next, we are going to look at the half equivalence point. That's where a buffer is made. Just memorize that. Buffers are made at the half equivalence point. What does that mean? It means you've used half of your weak acid, which means you've created an equal number of moles of your conjugate weak base. So those two numbers are going to be equal. In the case of our example, it was 0.5 moles of both. So you use the Henderson-Hasselbalch. Since you have some of both the weak acid and the conjugate weak base, you use Henderson-Hasselbalch. And if those two numbers are equal, then the base over the acid will equal 1, and the log of 1 is 0. So that means you want to create, this is really the key point of buffers. You want to choose an acid that has a pKa value that is equal to the pH that you want to buffer at. So if you want to buffer at 4.75, that's the pH you want to buffer at, then you choose the conjugate, you choose an acid with acetic acid which has a pKa of 4.75. And you put equal amounts in, equal concentrations, and that will be your buffer point. Okay? So that's a key point to creating buffers. Okay, the area over there on the left, the low side of the S curve, that's called pre-equivalency. It's before you get to the equivalence point. Both weak acid and conjugate weak base are present, and since you have both of them, you can use Henderson-Hasselbalch. That's the equivalence point right there. The equivalence point, all the weak acid, it's where all the weak acid, your weak acid defenders have been consumed. You have at that point no weak acid and no strong base, OH. So now you don't have any weak acid, so you cannot use the weak acid equation. You have to use the weak base equation. If you don't know Kb, you have to compute it from the Ka or value, or from the pKa, well, from the Ka value. So there you see the equation. It's long, okay? It's the negative log of the square root of the Kb times the base concentration. And once you get that, that'll give you your pOH. Then you subtract 14 minus pOH will give you pH. And again, when it's a weak acid and a strong base, the equivalency is not going to be at 7. It's not going to be perfectly neutral, because you're going to have some of the conjugate weak base from your reactions in the solution. So the only thing driving the pH at that point is the conjugate weak base. In this case of the example, it was the acetate ion. Finally, up at the very top, you have post-equivalency. After that, at that point, all you have going into the solution is the strong base, so it's pushing the pH all the way up toward and to 14. So it's the negative log of the OH concentration. To get the pH, you subtract that from 14 and you get the pH. So that's a summary of all the different parts of a titration curve. Now this is for a strong base going into a weak acid. For a strong acid going into a weak base, we saw in a previous lesson that that S curve would be flipped around. Everything would be reversed. We're not going to go into that now. It's too much information at once. We'll talk about that later on in the spring. But it's really no different. It's no harder. It's no different. So how to create a buffer. Now that you know all that, it's pretty easy. Determine the pH at which you want the buffer to act. In the case of the last example, let's say it was 4.75. In the example of blood, it wants to be 7.35 to 7.45. So what you'd want to do is find a weak acid with a pKa between 7.35 and 7.45. But we'll go ahead and use acetic acid again, or hydrofluoric here actually. Select an acid with a pKa near the desired pH and the salt of its conjugate base. So we'll talk about that in class again. What does that mean? It means if you have a bunch of hydrofluoric acids, a very small number are going to dissociate into the fluoride ion. You're never going to have an equal number of hydrofluoric acids, HF, and F minus, the conjugate base, by continuing to drop hydrofluoric acid molecules into the solution. But you want to have equal numbers, so how do you do it? Well, what you do is you take a neutral molecule called a salt of a conjugate base, and instead of putting a proton onto the fluoride ion, the F minus, you put something else that has a positive charge that's not a proton. And that would be an alkali metal, such as sodium or potassium. And when you attach that to the fluoride ion, you have a neutral salt, what's called a salt. It's neutralized. And what you can do is go get a bottle of sodium fluoride, put it in the water, and one thing we know about sodium from solubility rules is it will immediately break off, go off to the side, and you'll have your fluoride ions. So you're able to add fluoride ions without adding hydrofluoric acid molecules. And that will give you equal numbers of the weak acid, hydrofluoric acid, and its conjugate weak base, the fluoride ion. Okay, we'll talk about that more in class. So it says select an acid with a pKa near the desired pH and a salt of its conjugate base, or select a base with a pKa near the desired pH and a salt of its conjugate acid. So example, with the one I just gave, let's do it again. For hydrofluoric acid, HF, the H plus will be replaced with an alkali metal such as sodium. That gives you a salt, a neutralized base. It's called a basic salt, and that's sodium fluoride. So that's a neutral molecule. You can go get a bottle of sodium fluoride out of a storeroom in chemistry. You can't get a bottle of fluoride ions. You can't have ions in a bottle. You can't do it. So you got NaF When you put that in the water, the Na ion will completely dissociate in water, see the solubility rules, leaving the conjugate base F- in solution in equal numbers to the acid HF. And that's what you want with a buffer, is equal numbers of the weak acid and the conjugate weak base. And then 3, determine the number of moles of buffer you would like to have. That just depends on, okay, how much acid, strong acid invaders do you expect to come in, or how much strong base invaders do you expect to come in. That will determine how many moles of the buffer you create. So example, you wish to buffer a solution at a pH of 4.75. What would be a good choice for the acid for this buffer? Using a table of pKa for different acids, look for one with a pKa at or near 4.75, or from a list of Ka values, find an acid with a Ka around 10 to the -5th. Remember, we did that little exercise with pHs, and I gave you concentrations of hydronium ions, and I said try to guess what the pH would be. It's the same thing here. If you want a pKa that's around 5, then you pick a Ka value that's around 10 to the -5. That will give you that. So here is one from a table that I gave you. I just snipped a little piece of it. So there's acetic acid, and you can't see the headings, but the 1.76 times 10 to the -5th is the Ka value, and the 4.75 is the pKa value. Now your book does not give you a table of pKa values, you only Ka values. So you have to learn how to recognize a pKa value from a Ka value. So by using equal concentrations of acetic acid and a conjugate base salt, such as potassium acetate or sodium acetate, again that's the neutralized base, a buffer for a pH near 4.75 can be achieved. And then determine how much buffer is needed and apply equal amounts of the weak acid base pair. And that's it. That's how you create a buffer. And that takes care of this lesson. A little bit long, but they're all going to be from now on. That's why you got to get on top of these. Okay, we're coming down to the wire. So please get this in. We're going to do a lesson similar to this. We did a lesson similar to this in class. And we're going to move on and do one more lesson on acid-base buffers and move on to a new topic. All right, have a great day. We'll see you on the next lesson.